Right at the height of the Cold War, in Cape Canaveral, Florida, sits Launch Complex 12. It was completed back in 1958, but on the morning of July 22, 1962, it was about to witness something historic, or at least, it was supposed to be historic. To put humanity on a trajectory toward Venus for the first time, NASA had commissioned the Jet Propulsion Laboratory to build a spacecraft that would accomplish something no American probe had ever done: conduct a planetary flyby of another world. In the background looms a massive Atlas Agena rocket, a 2.5-stage behemoth standing over 100 feet tall, fueled with liquid oxygen and kerosene in the first stage, and hypergolic nitric acid and UDMH in the upper stage. It's an engineering marvel containing 54,000 individual components, weighing 447 pounds, costing $18.5 million in 1962 dollars. That's roughly $180 million today. And when you add the full program costs, we're talking about $370 million in modern money. At 9:21 a.m. Eastern Time, the Atlas engines roared to life. For the first 293 seconds, it looked like everything was going according to plan. But then something went wrong. The rocket began to veer off course, fishtailing through the sky like a car on an icy road. Controllers on the ground watched in horror as their carefully planned trajectory dissolved into chaos. The range safety officer had 6 seconds to make a decision. 6 seconds before the Mariner spacecraft would separate from its booster, after which it could never be destroyed. He pressed the destruct button. $18 million evaporated in a fireball over the Atlantic Ocean. The root cause of this disaster: a lone missing character in hand-transcribed mathematical code. One tiny symbol, omitted by a technician at Cape Canaveral, that would later be immortalized by science fiction author Arthur C. Clarke as the most expensive hyphen in history. Except it wasn't actually a hyphen, and that's where our story really begins. Somewhere in a building at Cape Canaveral, in the weeks before launch, a technician sat at a desk with handwritten mathematical equations spread before him. His job was simple: transcribe these equations into the guidance computer, letter by letter, symbol by symbol. He had no reason to believe he'd just made a mistake that would cost $18.5 million. No reason to think that one symbol he missed, one tiny horizontal line over a letter R, would send a rocket tumbling out of control into the Atlantic Ocean. No alarm bells went off. No warnings appeared. The code was entered, reviewed, approved, and loaded into the system. And Mariner 1 rolled out to the pad, carrying within its guidance system a ticking time bomb that wouldn't explode until 293 seconds into flight. But we're getting ahead of ourselves. The space race. When the United States announced its intent to launch artificial satellites in 1955, the USSR countered by declaring that it would explore space in the near future. 2 years later, on October 4, 1957, the Soviets launched Sputnik Tharsin into the annals of space history, becoming the first artificial satellite to orbit Earth. Not to be outdone, the United States passed the National Aeronautics and Space Act in 1958, and NASA began operations. But the Soviet Union wasn't done. In 1961, cosmonaut Yuri Gagarin became the first human to enter space and return safely to Earth, a stunning propaganda victory that sent shockwaves through Washington. The following month, President John F. Kennedy delivered his famous Urgent National Needs speech to Congress, pledging not only to land men on the moon by the end of the decade, but to devote unprecedented resources to NASA in pursuit of scientific advancement. Part of this initiative was the Mariner program, a series of 10 unmanned spacecraft designed for interplanetary exploration. With a total budget of $554 million, the program set out to accomplish a set of ambitious directives, beginning with Venus. Venus, our sister planet, is roughly the same size as Earth and our closest planetary neighbor at its nearest approach. But unlike Earth, Venus is shrouded in thick, opaque clouds that completely hide its surface from view. Scientists in the early 1960s knew virtually nothing about what lay beneath those clouds. The only way to find out was to send a spacecraft there. Building Mariner. The original plan called for a purpose-built probe called Mariner A, a hefty 1,250-pound spacecraft to be launched using the Atlas Centaur rocket. The Centaur was a revolutionary new upper stage that used liquid hydrogen, offering far greater performance than any previous rocket. There was just one problem. The Centaur wasn't ready. Development problems plagued the Centaur program throughout 1961 and early 1962. JPL proposed a solution: adapt the spacecraft from their ongoing Ranger lunar program. The Ranger Block Y spacecraft had already been designed and tested, and while it was lighter and less capable than the planned Mariner A, it could be launched on the available Atlas Agena B rocket. NASA accepted the proposal, and JPL began an 11-month crash program to develop Mariner R, so named because it was a Ranger derivative. The resulting spacecraft was a masterpiece of efficient engineering. It consisted of a hexagonal base, 1.04 meters across and 0.36 meters thick, containing 6 magnesium chassis housing all the electronics. On top sat a tall pyramid-shaped mast, bringing the total height to 3.66 meters. 2 rectangular solar panels with a total span of 5.05 meters provided power, while a large directional dish antenna extended below the spacecraft. The total weight came to exactly 447 pounds, within 3 pounds of the design specification. The spacecraft carried 46 pounds of scientific instruments, including a microwave radiometer to measure Venus's surface and cloud temperatures, 2 infrared sensors, a 3-axis magnetometer, a cosmic dust detector, a solar plasma spectrometer, charged particle detectors, and a cosmic ray detector. Notably absent was a camera. With payload space at a premium, project scientists, over the objections of a young Carl Sagan, considered cameras an unneeded luxury that couldn't return useful scientific results since Venus's clouds would hide everything anyway. The launch window. The launch window for Mariner was constrained by 2 factors. First, orbital mechanics meant Earth and Venus needed to be in the right positions relative to each other, creating a 51-day window from July 22nd through September 10th, 1962. Second, only Cape Canaveral Launch Complex 12 was available for Atlas Agena launches, and it took 24 days to ready an Atlas Agena for launch. This meant NASA had only a 27-day margin for error for a 2-launch schedule. The guidance system. The Atlas Agena relied on a sophisticated guidance system that involved multiple components working together. The Atlas Airborne Rate Beacon transmitted the rocket's angular velocity back to ground stations. A ground-based track system used radar to measure the rocket's position and angle. The Burroughs guidance computer at Cape Canaveral received data from both systems and calculated steering commands, which were then sent back up to the rocket via radio. The system was designed with built-in redundancy. If one radar failed, the other could theoretically maintain guidance. But there was a problem. The rate system measuring velocity and the track system measuring position had a slight timing mismatch, a 43-millisecond delay between their data reports. This wasn't a problem by itself. The Cape computer was programmed to correct for this difference, but in that correction process, a hidden bug was lurking. To handle the timing difference, the ground computer ran the rate system data through a mathematical formula, a data editing program that would smooth out minor variations and account for the timing delay. This formula was supposed to contain instructions that would tell the computer, if the rate beacon fails completely, ignore its data and use the track system instead. The formula involved something called a smoothing function, a way of averaging out random noise and minor fluctuations to get a cleaner signal. In mathematical notation, this smoothing function was represented by a symbol that looked like this, R, with a horizontal bar over it. This is called an overbar or vinculum, a standard mathematical notation meaning the smoothed or averaged value of R. Specifically, the formula was meant to represent the nth smoothed value of the time derivative of a radius r, in plain English. take multiple measurements of how fast the distance is changing, average them together, and use that smoothed value. The problem was that when the flight equations were originally written out by hand on paper, they included the correct symbol, R bar. But when a technician at Cape Canaveral transcribed these handwritten equations into the computer program, he missed the overbar. He entered just R. Without the overbar, the program would use instantaneous, unsmoothed values instead of averaged values. Why it mattered. Now here's where it gets catastrophic. The rate beacon on Mariner 1's Atlas didn't just have a typo in its software. It also had a hardware failure. At approximately 140 seconds into the flight, right around the time the booster engine separated, the Atlas airborne rate beacon malfunctioned. It failed 4 separate times during the flight, for periods ranging from 1.5 to 61 seconds. This shouldn't have been fatal. The system was designed with redundancy to handle exactly this situation. The perfect storm. When the rate beacon failed, the system was supposed to detect the failure, ignore the rate beacon data, switch to using only the track system data, and continue guidance using position and angle measurements alone, and it tried to do exactly that. But here's what actually happened. During the periods when the rate beacon was inoperative, the ground receiver was still scanning, trying to find the beacon signal. As it scanned through different frequencies looking for the signal, it generated what's called a sweep frequency, essentially noise from the search process itself. The buggy program, lacking the instruction to ignore missing data, treated this sweep frequency as if it were real velocity data from the rate beacon. Then it combined this garbage data with the legitimate tracking data from the track system. Then it calculated guidance commands based on this combination of real data and noise. Then it sent those commands up to the rocket. The Atlas began receiving steering commands to correct for problems that didn't exist. "You're veering left," the computer told the rocket, even though it wasn't. The Atlas dutifully corrected to the right. "Now you're veering too far right," the computer insisted, though the earlier command had started a real drift. The Atlas corrected back to the left. With each correction based on false data, the rocket's actual trajectory grew more erratic. It began to fishtail, overcorrecting in one direction, then overcorrecting back, in an ever-worsening oscillation. By 265 seconds into the flight, about 4 minutes and 25 seconds after launch, the oscillations had become severe. The Atlas executed what NASA's official report called an unscheduled yaw-lift maneuver, a sudden, violent rotation to the northeast that was never supposed to happen. Controllers on the ground could see what was happening, but they were powerless to stop it. The rocket was still following commands, just the wrong commands, generated by bad math operating on garbage data. The range safety officer's job was singular and clear. If a rocket threatens populated areas, destroy it. He watched as the Atlas deviated further and further from its intended trajectory. Radar tracking showed it was now on a course that would take it toward either the North Atlantic shipping lanes full of commercial vessels or inhabited areas of the eastern seaboard. At 287 seconds, 6 seconds before the Agena would separate from the Atlas and destruction would become impossible, the range safety officer made the call. He sent the destruct command. The Atlas Agena exploded over the Atlantic Ocean. The Mariner 1 spacecraft, its scientific instruments still functioning, continued to transmit telemetry data for another 64 seconds as it tumbled toward the sea. Then silence. $18 million, years of work, and thousands of person-hours, all gone in an instant. All because of a missing overbar in a line of code. Finding the bug. Within hours of the failure, NASA and JPL engineers began their investigation. The destruction happened so quickly that some initial speculation focused on mechanical failures, perhaps the Atlas engines, or the guidance gyroscopes, or the rate beacon hardware. But telemetry data told a different story. The Atlas engines had performed perfectly with nominal thrust levels throughout. The physical steering mechanisms worked correctly. They were just receiving bad commands. The rate beacon had indeed failed multiple times, but that shouldn't have been catastrophic. Something was wrong with the guidance logic itself. After 5 days of intense post-flight analysis, JPL engineers determined what had caused the malfunction: an error in the guidance computer logic combined with a hardware failure. Specifically, the omission of a superscript overbar when translating the handwritten equations into the coded computer instructions allowed transmission of incorrect guidance signals to the spacecraft when the airborne beacon was inoperative. The bug was so obvious in hindsight that it was almost embarrassing. An experienced programmer could have spotted it in minutes, if they'd known to look for it, but nobody had known to look for it, because it had never caused problems before. The Atlas Agena had been used for multiple previous missions, including the Ranger lunar probes. Why hadn't this bug shown up before? The answer: pure luck. In the previous launches, the rate beacon either worked perfectly with no failure to trigger the bug, or failed only briefly, so the bug didn't have time to cause catastrophic deviation. Mariner 1 was simply the first launch where the rate beacon failed for long enough, at a critical enough moment in the flight, to expose the latent software error. Lessons learned. The Mariner 1 failure led to immediate and lasting changes in how NASA approached software development. The bug was identified within 5 days, and the fix was straightforward. Add the missing overbar to the code engineers also implemented additional safeguards. More robust failure detection with better logic for distinguishing true failures from noisy data. Sanity checks that would reject physically impossible guidance commands. And manual override capabilities giving ground controllers direct control if automated guidance started behaving erratically. Mariner 2. Redemption. With the bug identified and fixed, NASA moved quickly. Mariner 2 was already built and ready, sitting in the vehicle assembly building at Cape Canaveral, waiting. On August 27, 1962, just 36 days after Mariner 1's destruction, Mariner 2 lifted off from the exact same pad, Launch Complex 12. This time, everything worked. The Atlas performed flawlessly. The rate beacon worked mostly, and even when there were brief glitches, the corrected guidance software handled them gracefully. For 110 days, Mariner 2 journeyed through interplanetary space, farther from Earth than any human-made object had ever traveled with a working communications link. On the way, it made history. First spacecraft to measure the solar wind, confirming its existence and constant flow, measured interplanetary magnetic fields, detected high-energy charged particles from solar flares, measured cosmic rays from outside the solar system, and found that interplanetary dust was scarcer than predicted. At 19:59:28 UTC on December 14, 1962, Mariner 2 passed within 34,773 kilometers of Venus, the closest any spacecraft had ever come to another planet. For 42 minutes, its instruments scanned the mysterious shrouded world. The data they sent back revolutionized our understanding of Venus. Surface temperature of 500 degrees Celsius, hot enough to melt lead. Crushing atmospheric pressure about 90 times Earth's primarily carbon dioxide atmosphere. Cloud tops at about 60 kilometers altitude. Slow retrograde rotation where one Venusian day is longer than its year. No detectable global magnetic field. And no Van Allen radiation belts. Before Mariner 2, some scientists had speculated Venus might be a warm, tropical world beneath its clouds, perhaps even harboring life. The data destroyed that romantic notion forever. Venus was a hellish greenhouse with temperatures hot enough to vaporize water and atmospheric pressure strong enough to crush a submarine. Mariner 2 became the first spacecraft to successfully encounter another planet and return scientific data. It proved that interplanetary travel was possible, validated NASA's approach to automated space exploration, and redeemed the Mariner program after the devastating failure of Mariner 1. Other victims of simple errors. The Mariner 1 incident is far from unique. The history of spaceflight and computing is littered with disasters caused by tiny mistakes. The Mars Climate Orbiter in 1999 cost $125 million and flew off course because one team used metric units, while another used imperial units. A simple unit conversion error. The Ariane 5 Flight 501 in 1996 cost $370 million when the European Space Agency's rocket self-destructed 40 seconds after launch, because a 64-bit floating point number was converted to a 16-bit signed integer, causing an overflow that crashed the computer and exploded the rocket. The human cost. There's another dimension to the Mariner 1 story that rarely gets discussed: the human toll. Imagine you're the technician who transcribed that code. You did your job. You entered the equations as carefully as you could. You had no reason to think anything was wrong. Then one morning, you wake up to headlines: "For want of hyphen Venus rocket is lost." Your mistake, a single missing character, just cost $18.5 million and America's first chance to reach another planet. Everyone at NASA knows. Your colleagues know. Your family sees the news. How do you live with that? We don't know what happened to that technician. NASA never released his name. Did he continue working in the space program? Did the guilt drive him out of the field entirely? Did his colleagues support him or shun him? Did he ever forgive himself? In some organizations, mistakes like this end careers through public shaming, termination, and blacklisting. But the best organizations recognize that mistakes are inevitable, and the right response is to learn from them, not to punish the individual, but to fix the system that allowed the error to occur. NASA, to its credit, seemed to take the latter approach. The Mariner 2 launch happened just 36 days later. They didn't spend months looking for scapegoats. They found the bug, fixed it, and moved forward. Somewhere in the aftermath of Mariner 1, a team of JPL engineers spent 5 days poring over telemetry data, flight logs, and computer printouts. One of them spotted it. One of them realized, "Wait, the overbar is missing. We don't know their names either. They saved Mariner 2. They saved the program. They might have saved careers. But they're anonymous footnotes in history." While Arthur C. Clarke's catchy phrase, "the most expensive hyphen," lives on, the legacy. Today, if you visit the Jet Propulsion Laboratory in Pasadena, California, you'll find displays commemorating the Mariner missions. Mariner 2 gets pride of place. The first successful interplanetary spacecraft, Mariner 1, is a footnote. But ask any aerospace engineer about the most expensive hyphen in history, and they'll know exactly what you mean. It's become a legend, a cautionary tale, a reminder of human fallibility, an illustration of why details matter, and perhaps most importantly, an example of how to handle failure with grace. Because NASA didn't hide the mistake, they didn't fire everyone involved. They didn't give up on Venus. They found the problem, fixed it, and tried again, and they succeeded. That's the real legacy of Mariner 1. Not the expensive hyphen, not the missing overbar, not even the spectacular explosion over the Atlantic. The legacy is resilience. The willingness to fail, learn, and try again. The courage to push boundaries knowing that sometimes you'll fail. The wisdom to learn from mistakes rather than hide them. And 63 years later, we're still exploring the solar system because of lessons learned from failures like Mariner 1. Thanks for watching.